Good day everyone. In this video, we're going to discuss lesson 6.3. This is all about spline interpolation. This is under module 6, which is all about interpolation, least square approximation, curve fitting, and optimization. Your takeaway for this lesson is first, you will be able to determine the equation of given data points by using the method of spline interpolation. And then you'll be able to estimate also new data point between or outside a given set of data points using the equation generated by spline interpolation. Now, why do we need to study spline interpolation, or why do we need to use spline interpolation for our given data set? Now, the previous methods of interpolating datasets using polynomials lead to erroneous results because of round-off error and overshoot. Using a spline would address these problems, and it is superior to higher order interpolating polynomials in some applications. Say for example, if this is our f of x, which is a step function, this will be the uh, polynomial, a spline polynomial that estimates this given function. Now, if we're going to increase the degree of our spline, it will look like this until such time it will follow the behavior of our step function. So it eliminates this overshoot right here. Now, what is spline interpolation then? So the concept of a spline originated from the drafting technique of using a thin, flexible strip called spline, as you can see in this figure, to draw smooth curves through a set of points. In this figure, we have one, two, three, four, five distinct points. And our spline right here, which is a thin, flexible strip, runs along these distinct points. So spline interpolation, like polynomial interpolation, also involves several orders or degrees, such as the linear spline with a degree equal to 1, the quadratic spline with degree equal to 2, and a cubic spline with degree equal to 3, and so on and so forth. Now let's start for the linear spline interpolation. By the way, for this video, I will only discuss you the two spline interpolations. These are the linear spline and the quadratic spline. Now for linear spline interpolation, this is the simplest connection between 2 points is a straight line. Of course, we already know that one. So the first order splines for a group of ordered data points can be defined as a set of linear functions. When we talk about spline interpolation, it involves several functions. For linear, so we have a set of linear functions. Say, for example, in our Cartesian or on our Cartesian coordinate plane, we have here um, n distinct number of points, starting with x naught, f of x naught. So this is the coordinates of our first point. Then this one is our second point, whose coordinates x1 and f of x1. By the way, f of x1 is simply our dependent variable, or the variable y. And we also have our last data point, whose coordinate is xn and f of xn. Now we are going to connect these data points by a line, as you can see. Now these are the linear functions that are being generated from the given graph. So for the first line, which is this one, connecting x naught and x1, we have f of x is equals to f of x naught plus the slope times x minus x naught. Now our first linear function is only valid within this given domain, that is from x naught to x1 only. inclusive. And by the way, this formula comes from the formula for a line from y minus y naught is equal to the first or the initial slope times x minus x naught. Now for the second line, you have this second linear function with given domain and so on and so forth. And by the way, in solving for the slope, you are going to use this formula. So the slope for any given linear function is equal to the change in y over change in x, or that is equal to f of x I plus 1, which is the next y value minus f of xi, which is our current y value, all over xi plus 1, which is the next x value of the given data point, minus xi, which is the current value of our given data point. Now, let's have some example. So, fit the data in the table on the right. So, we have for the x column 3, 4.5, 7, and 9. And we also have the f of x column or the y column. So, for 3, the y value is 2.5. For 4.5, the y value is 1. For 7, that's 2.5. And lastly, for x is equals to 9, the y value is 0.5. We are going to fit a first order spline, that is a linear spline, out of these given data points. And then once we generate the linear functions, we are going to evaluate the function at x is equals to 5. So what will be the value if x is equals to 5? As you can see from the given table, we don't have an information that will give us the value of x is equals to 5 because we only have 3 and 4.5 and also 7. That is why we need an interpolation. And for this example, we will use the linear spline. Okay, this is how you are going to solve this problem. First, we are going to plot the given data points on our Cartesian coordinate plane. So these are the points. We have 3 and 2.5 for the initial point denoted by naught. Then the second point has coordinates 4.51. Then the third point we have 7 and 2.5. And then the last point has coordinates 9 and zero point 0.5. So the coordinate system, by the way, is in x, comma, y form. Next, we are going to connect these data points by a line. So for the first line, it has a linear function of the form f1 of x is equals to f of x naught plus m1 times x minus x naught on the interval 3 until 4.5 inclusive. Then for the second line, this is the format of its linear function, and this is its domain. And then for the last line, this will be its format of its function, and this is its domain. Next, we're going to solve uh, for the functions, for the three functions, starting with the first one, f1 of x. So this is the format of our first function with domain from 3 to 4.5 inclusive. Now, as you can see, f of x naught is already defined and also the value of x naught. So we're only um, our problem is only the value of our slope m1. Now the points of interest for the first function, we have the 2 points 3 at 2.5 and 4.51. Now we're going to get the slope using these 2 points. So we have m1 is equals to the change in y over change in x. The change in y, that is from point 1 to point naught, all over x1 minus x naught. Then we're going to input the values. So we have 1 minus 2.5 all over 4.5 minus 3. And if you're going to input this one in your calculator, you'll arrive a slope equal to negative 1. Therefore, the equation is f1 of x is equal to 2.5. So 2.5 is the value of our y for our first point. Then minus the slope times x minus 3. Afterwards, you are going to simplify this one so that you will arrive the final form for our first linear function. And this is f1 of x is equals to negative x plus 5.5. Now the negative here indicates that this line slopes downward. Next, we will proceed to the second linear function. So this is the format of our second linear function, and this is its domain. The points of interest for this one are the points 4.51 and 7.2.5. Next is you're going to get the slope. So m2 is equal to delta y over delta x. And then you're going to substitute the values for y2, y1, and x2 and x1. And you're going to input this one in your calculator, and you will arrive a value of your second slope that is equal to zero point 0.6. Therefore, substitute the values of your slope as well as the value for y and x. So you will have f2 of x is equal to 1 plus zero point 0.6 times x minus 4.5. Then simplifying this equation, you will arrive the final form for your second linear function. f2 of x is equal to 0.6x minus 1.7. As you can see, we have a positive coefficient for our x, which indicates that this line slopes upward. And lastly, we're going to solve for the third function. So this is the format of the third function, and this is its domain. The points of interest has coordinates 7, 2.5. So this is for the third point, and our last point has coordinates 9 and 0.5. Now to solve for the slope, we have m3 is equal to delta y over delta x. Then substitute the values for y3, y2, and x3 and x2. And you will arrive a slope which is equal to negative 1. Therefore, substitute these values, the slope and the values for y and x. You will arrive f3 of x is equals to 2.5 minus 1 times x minus 7. And then simplify this one further. So you will get the final form of our third linear spline function, f3 of x is equal to negative x plus 9.5. So since we have a negative coefficient value for our x, this indicates that this line slopes downward. To summarize, so this is our first linear spline, this is our second linear spline, and this is our third linear spline. The last requirement is to evaluate the function at x is equal to 5. So we're going to solve for f of 5. Now we're going to select the second linear spline. It's because the x is equals to 5 belongs to the interval 4.5 is less than or equal to x, and x is less than or equal to 7. Now we're going to use this linear spline equation. Substituting x equals to 5, we have f2 of 5 is equals to 0 0.6 times 5 minus 1.7. Evaluating this expression will give us the value of our f2 of 5, that is equal to 1.3. Next, we will proceed to our second example for linear spline. The statement is fit the data in the table below or table on the right with the first order spline. Next is we're going to evaluate the function at t is equals to 210 degrees Celsius. Now, for this example, we're given with a table whose first column is for the temperature in degrees Celsius, and the second column is for the values of the enthalpy at corresponding temperature. So the enthalpy is in kilojoules per kilogram. That is, for 100 degrees Celsius, the enthalpy is 2,258 kilojoules per kilogram, And at 400 degrees Celsius, we have an enthalpy of 2001 kilojoules per a kilogram. Now, the first step is to plot these data points on our Cartesian coordinate plane with horizontal axis for the temperature and the vertical axis for the enthalpy. And these are the points. So the initial point has coordinates 100, 2258. Then the second one, 200 and 1045. The third one is at 300. We have an enthalpy of 2135. And lastly, we have 400 and 2001. This is our first line, and this is the format of its function, and this is its domain. For our second line, this is the format of its function. So h2 of t is equals to ht of 1 plus the slope times t minus t1. And this is its corresponding domain. And lastly, we have our third linear spline equation or function. We have h3 of t is equals to h of t2 plus the slope times t minus t2. And this is its corresponding domain. Next is we're going to derive the we're going to derive these three equations. So let's start with the first equation for enthalpy as a function of the temperature. So this is its format and this is its corresponding domain. The points of interest are the first 2 points. We have the 100, 2258 and 200, 1045. We're going to get the slopes. So the slope is equal to the change in enthalpy over the change in the temperature. So we have h1 minus h naught all over t1 minus t naught. The next step is you're going to substitute the values for the enthalpies and the temperatures. And then if you're going to input these values in your calculator, you will arrive the slope of your first line, which is equal to negative 12.13. Therefore, if you're going to substitute the values of your slope as well as for the enthalpies and the temperature, you will arrive an equation for your first line equal to 2258 minus 12.13 times t minus 100. Next, you're going to simplify this one so that you will arrive the final form for your first linear spline. You have h1 of t is equal to negative 12.13 t plus 3471. So the negative here indicates that this line slopes downward. Next, we will proceed to the second um, linear spline for the enthalpy as a function of time. So this is its format and this is the domain. The points of interest for this one are the second and the third point whose coordinates are 200, 1045 and 300, 2135. Next, solve for the slope using this formula. M2 is equal to the change in enthalpy over the change in the temperature. So next is substitute the values for the enthalpies for points 1 and 2 as well as the temperatures. And you will arrive a slope equal to 10.9. Next, you're going to substitute the values of your slope and the values for and your enthalpies and temperatures. So you will arrive h2 of t is equal to 1045 plus 10.9 times t minus 200. Next is simplify the equation so that you will arrive the final form for your second linear spline. That is h2 of t is equal to 10.9 t minus 1135. Lastly, for the third linear spline, h3 of t. So this is the format and this is its domain. Now the points of interest here are the third and fourth points whose coordinates are 300, 2135 and 400, 2001. Next, solve for the slope. So M3 is equal to the change in the enthalpy over the change in temperature. So same as the previous um, linear spline. So you're going to substitute the values for the enthalpies and the temperatures, and you will arrive a slope equal to negative 1.34. Then substitute the values. So you will arrive this equation, and simplifying this one further, you will arrive the final form for the third linear spline h3 of t is equal to 1 -1.34 t plus 2537. To summarize, this is our first linear spline for the enthalpy as a function of time. This is the second, and this is the last. Next, we're going to evaluate the function at a temperature equal to 210 degrees Celsius. That is, we're going to solve for h of 210. Now, we're going to select the second linear spline equation since the given temperature, which is 210 degrees Celsius, belongs to the interval 200 less than or equal to t and less than or equal to 300. And this domain is under the second linear spline equation. Now, this is our second linear spline equation. We're going to substitute t equal to 210. So we have 10.9 times 210 minus 1135. That will give us an enthalpy of 1154 kilojoules per kilogram. So this is the enthalpy at a temperature of 210 degrees Celsius. Now, uh, there are some disadvantages of using linear spline interpolation. So the primary disadvantage of the first order splines is that they are not smooth. Now, at the data points where two splines meet, called a knot, so this one, these are the knots, the slope changes abruptly, which is unrealistic for the first ordered spline. So at the interior knots, it must be that the uh, line here behaves like a curve rather than a um, very straight line. So this is the improved version of our first order spline. So this is our second order spline, or also known as the quadratic spline. And further improvement for our quadratic spline or second order spline is our cubic spline shown right here. So we will proceed to the improved version of our linear spline, which is the quadratic spline interpolation. So for quadratic spline interpolation, the resulting system of equations for this method is of second order polynomial over a given interval. So to ensure that the mth derivative are continuous at the knots, by the way, as we go along with the steps for quadratic spline interpolation, we will meet some differentiations, especially at the interior knots. So for the mth derivative, this must be continuous at the interior knots. So a spline of at least m plus 1 order must be used. Therefore, we will adopt the quadratic spline because for quadratic spline, uh, it has a first derivative m equal to 1. Now, the objective in quadratic spline is to derive a second order polynomial or a second degree polynomial for each interval between data points. So the polynomial is of the form fi of x is equals to aix squared plus bix plus ci. So this is familiar because this is the format of a quadratic equation. And this is the degree, which is equal to 2. Now let's proceed to the steps for quadratic spline interpolation. So the steps are used to solve for the coefficients of each quadratic spline for each interval. So since we all know that the format for the quadratic spline involves um, two coefficients and one constant. So these are A, B, and C. Now make sure to note that for n plus 1 data points, there are n intervals. So in this figure, we have 1, 2, 3, 4, 4 data points. So therefore, expect 3 intervals. And for each of these interval, it has a corresponding quadratic spline equation. And for each quadratic spline equation, we have 3 unknowns. And these are the coefficients for x, for x squared, then x, and lastly the constant. So consequently, we have three intervals times three unknown for every equation that corresponds to a certain interval. So we have three n unknown constants, the a's, b's, and the c's. So this is our goal. As we go along with the steps, we are going to solve for the values of these unknown constants. Now, first step, the function values of adjacent polynomials must be equal at the interior knots. And these are our interior knots with coordinates x1, f of x1. Then the second interior knot, we have x2, f of x2. Now, for the first quadratic spline, this one, and the second, they have a common point at the interior knot number 1. And for the quadratic spline equations 2 and 3, they also have a common interior knot, which is equal to the interior knot 2, which means that if you're going to evaluate these two pairs of quadratic spline equations at x1, say for example, for 1 and 2, if you're going to evaluate these two equations at x1, you will arrive the same values for your y, and that is equal to f of x1. So to execute that one, so for the first quadratic spline equation, this is its format. At the interior knot number 1, whose coordinates x1, f of x1, you're going to substitute that one. So its y is equal to f of x1 is equal to a1, and for its x, that is x1 squared plus b1 times x1 plus c. So this is our equation 1. Take note, for 1, 2, 3, 4, 4 data points, we have 3 intervals, and then for every interval, uh, there is a corresponding number of quadratic spline equations as well. And for every quadratic spline equation, we have 3 unknowns. So in total, we have 9 unknowns for these 4 data points. So we will expect 9 equations. So this is our equation 1. Next, for the second quadratic spline equation, this one right here, this is its format. Now at the first interior knot, this is the coordinates. So we're going to substitute these values for x and f of x to our second quadratic spline equation. So we have here f of x1 is equal to a2 x1 squared plus b2 x1 plus the constant. So this will be our second equation. So we need 7 more equations. Next, we will proceed to the interior knot number 2. So for the interior knot number 2, the quadratic spline equations involved are 2 and 3. So starting with the second quadratic spline equation, this is its format. So at the interior knot number 2, uh, these these are the coordinates x and y. We're going to substitute that one to our second quadratic spline equation, and this will be our equation 3. Next, for the last quadratic spline equation, that is our quadratic spline equation number 3, this is its corresponding format. Then we're going to substitute the x and y values for our interior knot number 2, and this will lead to our fourth equation right here. Next, the second step is the first and last functions must pass through the endpoints. So this adds two additional equations. Again, these are our endpoints. We have endpoint number 1 at x naught f of x naught, and this is our endpoint number 2 at x3 f of x3. Now, the quadratic spline equations that um, that coincides these two endpoints are quadratic spline equation number 1 and a quadratic spline equation number 3 for the endpoint number 2. Now, for the first quadratic spline equation, as you can see in the graph, it coincides with the endpoint number 1. So therefore, at the first endpoint, we're going to substitute the values for our x and y to our first quadratic spline, and it will become f of x naught is equal to a1 x naught squared plus b1 x naught plus c1. So this will be our equation number 5. And for the last quadratic spline, if we refer from our graph, we can see that it intersects our endpoint number 2. So we're going to substitute the x and y values from our endpoint number 2 to our last quadratic spline. And this will be our equation number 6. The third step states that the first uh, derivatives at the interior knots must be equal. So these are our interior knots, interior knot number 1 right here, and interior knot number 2. Now, since at the interior knots, they have the same curvature, so they also have the same value for its first derivative, or they have the same slope at this point. So for the first and second quadratic spline equations, these are the formats of their um, equations. Now let's take the first derivative of each of these equations. So for the first quadratic spline, we have f prime of x is equal to 2a sub 1x plus b1. And for the second quadratic spline, we have f prime of x is equal to 2a sub 2x plus b2. So at the interior knot number 1, whose coordinates are x1 and f of x1, they have the same value for its derivative for both the first and second quadratic spline. So therefore, we're going to equate these two. We have f prime of x1, that is for the first quadratic spline equation, is equal to the first derivative of the second quadratic spline equation at x1. Substituting or writing the equivalent expression for the derivative. So for f prime of 1, you have 2a sub 1, then it's x is equals to x sub 1, so you have here x sub 1 plus b1 is equal to 2a sub 2 x1 plus b2. This is now our equation number 7. Now let's proceed to the second interior knot. So for the second interior knot, the quadratic spline equations involved are uh, 2 and 3. So these are the formats for the quadratic spline equations for 2 and 3. Now let's take the derivative, the first derivative of each of these quadratic spline equations. So for 2, you have f prime of 2 equals 2a2x plus b2. And for the third quadratic spline equation, we have f prime of x is equal to 2a3x plus b3. Now at the interior knot number 2, the slope of these two quadratic spline equations are equal to each other, or its first derivative are equal to each other. So we have f prime for 2 is equal to the f prime for 3. Now we're going to substitute the expression for their derivatives. So you have 2a2 times x2 plus b2 for the second quadratic spline, and 2a3 x2 plus b3 for the last or the third quadratic spline equation. And this will be our equation number 8. Now we only have one uh, equation to be determined because we need 9 equations, and we are now on the equation, or we have just um we have just determined the equation 8. So we only need one more equation in order to uh, determine the 9 unknowns. So for the last step, we'll assume that the second derivative is 0 at the first point. So the visual interpretation of this condition is that the first 2 points will be connected by a straight line, not by a curved line or a quadratic spline. So we will assume that the first two data points are connected by via a straight line. If this is the case, then for the first quadratic spline equation, this is its format. If we take the first derivative, the result is 2ax plus b1. Now, taking another derivative, or the second derivative, is f double prime of 1 is equal to 2a1. And then if our assumption is a straight line, so the second derivative for this one must be equal to 0. Therefore, a sub 1 is equal to 0. So we now have a value for our one of our unknowns. So this will be our equation 9. And to summarize that one, these are our 9 equations. So to solve for our 9 unknowns, so use any methods to solve for this. So you may use matrices. So you can have the Kramer's rule, the matrix inversion using inverse of a matrix and some multiplication, or you can also use the lower upper decomposition method. So it's up to you if which one of this method you think is comfortable for you to use in solving these unknowns. Okay, let's try some example. We have here problem statement. Fit the data in the table shown on the right, not below. Sorry, this is error. So with the second order spline. And afterwards, evaluate the function at x is equals to 5. Now, this is a similar data points from the example of the linear spline interpolation. So this time, we will evaluate this data using the second order spline. So for the solution, first is you're going to graph the given data points from the table on our Cartesian coordinate plane. So these are the 4 data points, and then we're going to sketch our spline equation or our spline. No? So for the first interval, this will be our first quadratic spline equation of the form f of x1 is equals to a1 x squared plus b1x plus c1. And this is our second quadratic spline equation with corresponding um, format of its equation. Then this is our last quadratic spline equation, and this will be its corresponding format. Now let's proceed to the first step. By the way, before that, let's have some important notes before those steps. So here, the number of intervals is equal to the number of quadratic spline equations. And I already showed that to you. So we have 1, 2, 3 intervals, and we also have 3 quadratic spline equations. Now the second statement, for every quadratic spline equation, there are 3 unknowns. So we have 3 unknowns multiplied by 3 intervals or 3 quadratic spline equations. We will expect 9 unknowns for A's, B's, and C's. Therefore, there are 3 by 3 or 9 equations needed in order to solve the 9 unknowns. Now, let's proceed to our first step. So for the first quadratic spline equation, this is its format. So at the interior knot number 1, we're going to evaluate the first quadratic spline equation whose coordinates for the interior knot number 1 are 4.5 for x and 1 for y. We're going to substitute these values. So we have here 1 is equal to a1, then the x is equal to 4.5 square plus b1 times x, which is 4.5 plus c1. Simplifying this one, you have 1 is equal to 20.25 a1 plus 4.5 b1 plus c1. So this will be our equation number 1. And for the second quadratic spline equation, so at the interior knot number 1, we have 1 is equal to a2 times 4.5 square plus b2 times 4.5 plus c2. Simplifying this one further, you will arrive your equation number 2. And that is 1 is equal to 20.25 a2 plus 4.5 b2 plus c2. Next, we will proceed to the interior knot number 2. So for the interior knot number 2, the quadratic spline equations involved are 2 and 3. So let's start with quadratic spline equation number 2. Now this is its format. We're going to evaluate this equation at the interior knot number 2, whose coordinates are 7 and 2.5. So substituting the values, you have here 2.5 is equals to a2 times 7 square plus b2 times 7 plus c2. Simplifying this one further, you will get uh, an equation for your equation number 3. Next, for the third quadratic spline equation, or the last, this is its format. So at the interior nut number 2, you're going to substitute the values for x and y to our last quadratic spline equation, so that you will arrive this expression 2.5, or this equation 2.5 is equals to a3 times 7 squared plus b3 times 7 plus c3. Simplifying this one, you will arrive your equation number 4. Next, uh, for the first quadratic spline equation, uh, this first quadratic spline equation um, will coincide to our first endpoint, which is right here, whose coordinates are 3 and 2.5. So let's substitute these values to our first quadratic spline equation. So you will have this 2.5 is equals to a sub 1 times 3 squared plus b sub 1 times 3 plus c1. Simplifying this expression will give you your equation 5. And for the last, or the third quadratic spline equation, this is its format. Then at the second endpoint, whose coordinates are 9 and zero point 0.5, so substitute this to your last quadratic spline equation. So you will have this equation 0 0.5 is equals to a3 times 9 squared plus b3 times 9 plus c3. Simplifying this further, you will arrive your equation number 6. Next, for the first and second quadratic spline equations, we all know that uh, their first derivative, or their slope at this point, is equal. So we will take the first derivative of each of these equations. So for the first quadratic spline equation, the first derivative is 2a sub 1x plus b1. And for the second quadratic spline equations, that is 2a sub 2x plus b2. So at the interior nut number 1, whose coordinates are 4.5 and 1, both the first derivative of the first and second quadratic spline equations are equal. That is why uh, I'm equating these two. Next, substituting the expression for both the first derivatives of the first and second quadratic spline equations, you have here 2a sub 1 times. Now the x value is evaluated using the value 4.5, so you have 2a sub 1 times 4.5 plus b1 is equal to 2a sub 2 times 4.5 plus b2. Now simplifying this one further, you will arrive this equation 9a1 plus b1 is equals to 9a2 plus b2. And this will serve as your equation number 7. Next, we will proceed to the second interior nut number 2. For the second interior nut number 2, the quadratic spline equations involved are 2 and 3. That is why for this step, we will get first the first derivative of the quadratic spline equations for the second and the third, and these are its corresponding expression of its first derivative. So at the interior nut number 2, whose coordinates are 7 and 2.5, both these two quadratic spline equations have the same first derivative or slope. So I equate them both and then substitute the expression for the first derivative. So for second quadratic spline equation, we have 2 times a2 times 7 plus b2. And for the third or last quadratic spline equation, I have here 2 times a3 times 7 plus b3. Simplifying this further, you will arrive 14a2 plus b2 is equals to 14a3 plus b3, and this will be your equation number 8. And lastly, we will assume that the spline that connects the first and second theta points is a straight line. So therefore, the second derivative of our first quadratic spline equation must be equal to 0. So we now have a value for a1 that is equal to 0. So this will serve as our equation number 9. Now to summarize, These are the list of our 9 equations for A's, B's, and C's from equations 1 to 3. Next step is we are going to convert this into an augmented matrix wherein we're going to list the coefficients for A1, B1, C1, A2, B2, C2, and A3, B3, C3, and lastly for the constant. So you have to arrange each of these 9 equations. So for our first equation, as you can see, the coefficients the coefficient for A1 is 20.25. So uh, it was also reflected in this table. Then for B1 is 4.5, then for C1 is equal to 1. So the rest from A2 to C3 are 0 because we don't have A2, B2, C2, A3, B3, and C3 for our first equation. And for the constant, so we have equal to 1. So we have here 1. Now, make sure that as you modify this or as you modify each of these 9 equations, see to it that the constant must be on the other side, not um, not on the side where the variables are located. Okay, so once you have generated the augmented matrix form, the next step is we are going to eliminate this last row. It's because it contains 0 and 0, 0, so that we can reduce the size of our matrix. Now this happens, it's because for our last equation we have A1 is equal to 0, so therefore all are also equal to 0. So if A1 is equal to 0, we are going to eliminate the first column as well. Okay, so this will be our final augmented matrix form, starting from B1 to C3 and the constant. Now, we are going to use the second method, that is the matrix inversion. For the matrix inversion, if we have matrix A that contains some constant times a column vector matrix X that contains the variables is equal to a column matrix that contains a constant equal to B. So solving for X, you will have the product of the inverse of A and the column matrix B. Now, the next step for this one is we're going to get the matrix A, X, and B. So this is our matrix A. Matrix A are the collection of the coefficients from B1 up to C3. Okay, and then we're going to multiply matrix A by our vector column matrix, which contains um, the unknowns starting with B1 until C3, and that is equal to our column matrix, that is our matrix B, that contains the constant values for each of the equations from 1 to 8. And the next step is to determine the inverse of matrix A. So this is the inverse of our matrix A. You can use an online matrix calculator to generate the inverse of matrix A, because if you're going to use cycle, this is not enough because the size of this matrix is enormous and our scientific calculator cannot deal with this anymore because we have 1, 2, 3, 4, 5, 6, 7, 8. We have an 8 by 8 matrix. So you need a software or uh, an online matrix calculator for this one. So having this inverse of matrix A, the next step is to use the formula for matrix inversion, that is to solve for X. You have X is equals to the product of the inverse of A times the column matrix B. So we have here the inverse of A times the column matrix B, and the result is our matrix X. So the first element for our matrix X corresponds to the value of our B1. Okay, that is why from the matrix X, so we have, again, I just write A1 here, so A1 equals 0. So B1 is equals to this one, negative 1. then C1 is equal to 11 over 2, and then for A2 that's 16 over 25, and this one is for our B2, and this one is for our C2, and then negative over 5 for our A3, 123 over 5 for B3, and lastly we have the negative 113 over 10 for our C3. Now we have the values for the coefficients as well as the constant. The next step is to generate the three quadratic spline equations. So these are the three quadratic spline equations. So we have f of x1 is equal to negative x plus 11 over 2. And notice that the degree of our first um, spline equation is not in a second order or a second degree. It's because uh, from our last step, we will assume that the spline that connects the first and the second data point must be a straight line. So it also conforms with the result of our uh, first quadratic spline equation. So our first quadratic equation, take note, this one is only valid within this given domain. And then the next one, this is the quadratic spline equation for our f of x2, and this one is for our f of x3. Now the next requirement is to evaluate the function at x is equals to 5. So for f of 5 right here, we're going to select the second quadratic spline equation, since x is equals to 5 belongs to the interval for the second quadratic spline equation, which is from 4.5 less than or equal to x to less than or equal to 7. Therefore, we're going to substitute the value for our x equal to 5 to our second quadratic spline equation. So we have here 16 over 25 times 5 square minus 169 over 25 times 5 plus 923 over 50. If you're going to input this one in your calculator, you will arrive a value for your f of 5 of 2, and that is equal to 0.66. Now, um, in order for you to understand what I have discussed here, you can practice using this exercise. So fit the data in the table below with the second order spline. Evaluate the function at a temperature equal to 210 degrees Celsius. So once you will follow all those steps, you will arrive these 9 linear equations. So from equations 1 until the last. Notice that the last one conforms with our last step, in which we assume that the spline that connects the first two data points is a straight line. So we have your a sub 1 is equals to 0. And once you have these 9 linear equations, the next step is to generate the augmented matrix. And after that, you will also generate the matrix for A, and then use any software or online matrix calculator to solve for the inverse of the matrix, and you will arrive this um, this matrix. Okay, so this is the inverse of the matrix for A, and after that you're going to perform the matrix calculation. So this is the inverse matrix for A. This one is for the column matrix for our constant, and this one right here are the values for the coefficients and the constants for A's, B's, and C's, excluding A1. And after that, you will uh, arrive these three quadratic span equations for the enthalpy as a function of the temperature. So this is our first quadratic span equation, but this is not actually a quadratic. This is a linear span equation because of our assumption from our steps, from one of our steps, or from the last step. And this is our second quadratic span equation and the third quadratic span equation. By the way, I forgot to put here the domain. So for our first spline equation, this is valid. from 100 to 200. For the second one, this is valid from 200 to 300. And this one is valid from 300 to 400. So that's it. And after that, evaluate the function at a given temperature equal to 210 degrees Celsius. So right here at T equals 210 degrees Celsius, the H using one of these three quadratic spline equations will give you 946.73 kilojoules per kilogram. Okay, and that's it for this video. I hope you learned something. So thank you and God bless.